So I wasn't exactly sure who would show up to this presentation, so hopefully in this presentation I will both insult you and go over your head in science, and so I want to apologize in advance. Before we get started, I also want to thank my gold team members. I think Deepak and Fazul and Kwan are here tonight, as well as our PI, Richard Eastes. So our universe is illuminated, and the light that we can see with our eyes is only a tiny fraction of the light that illuminates our universe. In fact, it's just a tiny part of the continuum of wavelengths, from radio waves, which span meters, down to gamma rays and X-rays. Basically, what I'm trying to tell you is light can be thought of as a wave, and waves have different wavelengths, and those different wavelengths have different properties. As a scientist, I take advantage of these different properties to explore the universe around us, and closer to home, our Earth. So how do we see these features if we can't see the entire wavelength of Earth, or the universe? Well, we build instruments to help us see for us. For example, most remote controls for our TVs use flashes of infrared light to communicate with your TV. This is light that our eyes are not sensitive to. This is on the wavelength side that is longer than our eyes are sensitive to. So how can you see this? Well, I think probably most of you guys brought your infrared detecting devices with you today. You can get out your smartphone and you can look at the TV remote control. So what you can do is look at the emitting end of your remote control, and you should see a dark eye. Let's see here, do I have other end? A dark eye right here, and then you can press any button on your remote control and you should see it light up. And depending on your detector in your smartphone, it should be illuminated in kind of a reddish purple color. We can turn these instruments to look at other portions of our sky, and we can see all sorts of interesting things. For example, this is the Crab Nebula. This is what it looks like in the optical wavelengths, but it's also a strong emitter in the radio, ultraviolet, and X-ray wavelengths. What powers these strong emissions is one of the most exotic objects known to modern astronomers. That's a pulsar. And the pulsar at the center of the Crab Nebula is a tightly packed ball of mass that spins at an amazing 30 times per second. We can also turn our instruments to look back at Earth. So you guys are probably very familiar with the visible wavelengths of Earth, where you can see the oceans and continents and clouds. But we can look at Earth in the infrared, which is IR, the same thing that I was talking about with your TV remote controls. And this gives us information on the water content, the water vapor content of Earth's atmosphere. We can also look at Earth in the far ultraviolet wavelengths. This is what gold looks at Earth in. There are a couple of reasons why we're interested in looking at Earth in the far ultraviolet. It can give us information on the temperature of the thermosphere. It can tell us about the plasma or ionized portion of our atmosphere and the ionosphere. And it can also tell us about the constituents that make up the atmosphere air, so the oxygen and nitrogen that's there. Another reason that we're interested in the far UV, which I probably should have mentioned, is between 120 to 200 nanometers, is that these wavelengths are opaque in the lower atmosphere. So that means that when we look at it from outer space, we have a nice dark background to look at, so that we can only see the upper atmosphere. So to kind of go backwards a little bit, I kind of want to explain a little bit about the upper atmosphere for those of you who aren't aware. We live in the troposphere down here. This is where the terrestrial weather that you and I are familiar with. So these would be your thunderstorms, your snowstorms, our rainstorms like we're having today. Above that is the stratosphere. This is where your commercial jets fly and the ozone layer exists. Above that is the mesosphere. This is where meteors ablate or burn up. And then finally you reach the thermosphere. The thermosphere starts at about 100 kilometers in altitude, or according to this little graphic, about 50 or 62 miles in altitude. And it contains phenomena such as the aurora, and it's also where low Earth orbiting satellites exist. So you have your International Space Station and those sorts of things. It goes all the way up to the exosphere. The exosphere is where gases exit the Earth's sphere of influence. So the thermosphere is the neutral portion of the far reaches of Earth's atmosphere where it meets space. Embedded within the thermosphere is the ionosphere. The ionosphere is where particles have become ionized or charged. And this usually happens by photoionization, where extreme ultraviolet light from the sun comes in and energizes whatever atoms or molecules are there, separating the electrons from the ions. The ionosphere and thermosphere are coupled, and that means that when you perturb the thermosphere, you also perturb the ionosphere, and vice versa. So GOLD, the mission that I'm going to be talking to you most about, observes the thermosphere at approximately 162 kilometers in altitude during the daytime and at approximately 300 kilometers in altitude at nighttime. And this has to do with the emission profile of the thermospheric emissions that we observe. The science that we're most interested in for GOLD can be split into two competing factors. The first factor is forcing that comes from above. So you can think of this as space weather that comes from the sun and comes into above the Earth's atmosphere. And then forcing that comes up from below. This is tropospheric weather that you and I experience that's percolating up. So from above, we're interested in how geomagnetic storms from the sun affect the thermosphere. And this is a model depiction of a geomagnetic storm impacting the Earth system. And then we're also interested in how the thermosphere responds to solar ultraviolet variability. And this is what the sun looks like in the ultraviolet wavelengths. From below, we have gravity waves, which I'll discuss a little bit later. So this is a model showing gravity waves percolating up from below, and also thermal tides. And then these forcings from above and below can meet and mix and create new kinds of physics and interesting phenomena in the nighttime equatorial ionosphere. And we're interested in seeing how that responds to these varying forcing factors. So at this point, you're probably saying, all right, she's talking about GOLD. What is GOLD? GOLD is the Global Scale Observations of Limb and Disk mission. It's a NASA mission of opportunity, which means it's hosted on a commercial spacecraft. In this case, it's SES-14, which is a communications satellite, which is located in geostationary orbit over the mouth of the Amazon River, which is approximately 47.5 degrees west longitude. The GOLD instrument consists of two identical independent imagers. So this is an artist's rendition of the GOLD instrument, and this is SES-14 right here. And this little bit right here is the GOLD instrument. So what we get from the GOLD instrument is daytime disk images of temperature and composition of the thermosphere and nighttime density of the ionosphere. And on Earth's limb, and when I say the limb, I mean this sort of gray halo around Earth, we can get temperature and density of the thermosphere in that region. So a little bit on the journey of the GOLD instrument to geostationary orbit. This is integration onto SES-14 in approximately April of 2017. You can see gold being lifted by a crane. And just for scale, you can see 4 engineers actually working on that satellite right there. So it's quite a large satellite that we're talking about. In October 2017, we had vibrational testing in Toulouse, France. And we do vibrational testing to basically imitate the launch environment that will be experienced by the satellite and the instrument, because we don't want pieces to break off or any catastrophic failures like that. And then finally, on January 25th, 2018 of last year, we were launched into orbit. We then had a 5-month cruise to geostationary orbit. Geostationary orbit is a very special kind of orbit. It's very difficult to get to. It's actually very expensive to get to. But what it's really special about it is the rate or the speed at which the satellite orbits the Earth is the exact same speed that the Earth is turning. So that means that when you look up at the satellite, it looks like the satellite is hovering above you in place. All right, so this is very valuable to communications satellites and companies that are streaming satellite TV and that sort of thing. Imaging from geostationary orbit really revolutionized the weather forecasting you and I are familiar with. We were able to see many days in advance what kind of weather systems were coming towards us. For example, this is an image from GOES 13. And when you, in the evening, see the news and they show a picture of the whole Earth, or maybe a hurricane in the Atlantic Ocean, what you're probably seeing is a GOES image. And all these GOES satellites are located in geostationary orbit. This one happens to be, I think, at about 75 degrees west, which is a little further west than where GOLD is located. But what's really exciting is GOLD is the first mission to image space weather from a geostationary orbit. And we're still in, I don't know if I'd call it infancy of forecasting space weather, but it's certainly immature. And we're really hoping that by collecting more data and more information about the thermosphere and ionosphere, we'll be able to better forecast space weather in Earth's atmosphere and also mitigate any impacts on our critical communication and navigation system. And the way we're going to do this is by producing images of Earth's disk every 30 minutes in the far UV. The GOLD instrument itself is what we call an imaging spectrometer. So this is a CAD drawing of the GOLD instrument. It has 2 identical channels, channel A and channel B. And if we were to cut channel B straight down the middle, we'd get a cross-section like this. So light enters the light shade from the left, bounces around a couple times inside the instrument, and then hits this very specialized diffraction grating. This diffraction grating splits the light into various light components, different spectral components, where it is finally imaged on a detector. From this, we get an image cube. And the way you can think of an image cube is a regular image has pixels that each have a vertical and horizontal location, right? In an image cube, each pixel also has spectral information, so different colors for each pixel. The way that GOLD scans the disk is that there is a slit that moves across the disk, just like being shown on the left-hand side of this animation. This slit is fully commandable, and its step rate is also fully commandable. So this means that if we see something of interest or something we want to study or do an experiment, we can actually tell it to just dwell in that one location or to scan small areas within that. On the right-hand side, this is trying to illustrate this image cube I was telling you about. So on the y-axis, we have what you can think of as latitude, and on the x-axis is wavelength. So this is the color information, the spectral information. We're going to cross into, so this is the day-night divider, and when we cross into night, we only have one wavelength left. This is the 135.6 oxygen color. And then when we cross into daytime, you'll see a whole bunch of other spectral information come up, and that's actually nitrogen colors that are excited nitrogen. The other thing you can see in this plot is information coming from the auroral regions, which will show up right here as a band of spectral information as well. So from these scans, what can we get? Well, in the daytime, we get a density ratio we call O to N2, which is a ratio. And this has really critical information for us to tell us about the upwelling of air within the atmosphere, so the vertical motion, as well as information on geomagnetic storms. We also get the temperature of the lower thermosphere. So in this temperature plot, we're getting the temperature in this region right here. At nighttime, we get the peak density and plasma of the ionosphere. So we're looking at this red line over here. At night, or on the Earth's limb, we get exospheric temperature. So that is the vertical portion of this temperature profile. And then we also get the O2 profile, so that would be the green line over here. All this data I'm about to show you is basically publicly available already. We've already published it. So this is your data. If you're interested in this, you can go and explore it. You can go and play with it. The GOLD website is this address right here. I never remember it. What I do is I usually just search GOLD, NASA, and UCF, University of Central Florida. And then you'll get to this web page. This is the quick look page, but we also have a download page. And what you can do is choose whichever date you're interested in, because say you're interested in equinox or solstice, whatever it may be, or maybe you know that there was a geomagnetic storm. Maybe you saw the northern lights for a particular geomagnetic storm, and you want to go and see what GOLD saw at that same date. Then you can select the observation type. We have daytime observations, we have limb observations, we have occultations, which means we watch a star as it sets behind the Earth. And we have nighttime observations, which is what I'm showing here. This nighttime observation is abbreviated as NI1. And you can download this and see what you can see in it. Right now we only have level 1 data products. Shortly we'll have level 2 data products. I will warn you though that if you download an entire day's worth of data, it's over 3 gigabytes. That's one of the great things about being on a communications satellite, is that our downlink is not as limited as in other situations. So after we completed our journey to geostationary orbit, we had our first full day of observations. And this was prior to finishing all of our commissioning activities. And we happened to be lucky enough to actually see a geomagnetic storm. This geomagnetic storm had a KP index of above 5, which is how we describe a level of activity for geomagnetic storms. And it began around 3 universal time, or about midnight local time for GOLD. And what we saw was, in this animation, you'll see that this is the oxygen to nitrogen ratio. And what we're interested in seeing here is there is a depletion, or a darker color, in the northern hemisphere. That means that the oxygen was depleted. And we were really happy to see this because it meant that our instrument was operating as we had hoped it would operate. But before we even launched gold, we did modeling studies to try and predict what we would see with gold. So this is some modeling I did with, so on the left column is gold observations for, I think it was December 15th of 2018. And on the right, we have modeling I did with a program called GLOW, which is a radiative transfer model of Earth's upper atmosphere that calculates the far ultraviolet emissions of our atmosphere. So to a first order, you can see that they look pretty good. When I say O5S, what I'm really talking about is the atomic oxygen 135.6 nanometer color. And when I talk about LBH, what I'm talking about is what are called the Lyman-Burge-Hopfield bands. And these are emissions due to nitrogen. So you'll see a couple of features in the observations that you don't see in the model. The first is well, I guess you do see in both of them the transition from day to night. But you might also notice that there's a strange discontinuity right here. And that's due to the fact that as the slit scans the northern hemisphere, there's a time differential between the time it scans the northern and the southern hemisphere. That's about 15 minutes. So you can actually see how much the Earth has changed in just those 15 minutes. The other thing you can see in the observations that are not in the model is some auroral activity in the northern hemisphere, and that's just because I didn't put any auroral activity into the model for that particular day. And then lastly, you can see some stars in the background that also emit in the far ultraviolet. And there are several of those stars that we're interested in. LBH, you can see some similar things. I will comment that the observations for the LBH color is rather noisy, and that's my fault in processing the data. I didn't do a very good job at removing the background noise there. All right, so now that I've tried to explain a little bit about gold and what we observe, I want to do kind of a left turn into the science that we can do with gold observations. This is a diagram that you might see frequently if you're in the astronomy community. It shows different waves that exist in our atmosphere. We have gravity waves, we have planetary waves, we have tides, we have gravity waves, we have planetary waves modulated by tides. The point is there's a whole soup of waves that exist in our atmosphere. And the reason we care is that the primary mechanism through which energy and momentum are transferred from the lower atmosphere where we live up to the upper atmosphere and ionosphere is through the propagation of these waves. Some of the waves that we're interested in are Kelvin waves, which also exist in the oceans. These do propagate into the thermosphere. They have timescales of 2 to 20 days, and their horizontal wavelengths are on the order of Earth's circumference. We also have Rossby waves, also known as planetary waves, whose restoring force is the potential vorticity, which is a fluid dynamics quantity. Up until now, we did not believe that they easily propagate into the thermosphere, but my colleague Quan Gan here has been doing some research recently with gold data that shows that we may actually be seeing planetary waves in the thermosphere. These have timescales of a couple days to maybe a month, and their horizontal wavelengths are on the order of 1,000 kilometers. Next we have thermal tides. These definitely do propagate into the thermosphere. These are one of the most prominent features of the thermosphere, and they have timescales that are fractions of a solar day. So you can have a third of a solar day, a half of a solar day, a whole solar day, that sort of thing. And their horizontal wavelengths are on the order of Earth's circumference. And finally, we have gravity waves. These also definitely propagate into the thermosphere. They have very short time scales, so we're talking on the order of minutes to hours, instead of days. And they have relatively short horizontal wavelengths, so we're talking tens to hundreds of kilometers in length. I'm going to talk mostly about thermal tides and gravity waves because they do the lion's share of coupling the lower atmosphere to the upper atmosphere, or transferring the energy and momentum from the lower atmosphere to the upper atmosphere. I'm trying to give you a beginner's primer on thermal tides in the upper atmosphere. A thermal tide is different than a gravitational tide that's excited by for example, the moon circling the Earth. A thermal tide is excited by heating in the atmosphere due to the sun. You could almost think of the atmosphere breathing a little bit when it encounters heating from the sun. And there's various sources from heating from the sun. So you can have latent heating in the troposphere, you can have heating due to ozone, and you can have heating due to oxygen in the upper atmosphere. I want you to try and have an ability, walk away with an ability to kind of visualize what maybe a thermal tide looks like in the upper atmosphere. So these are various tidal components. One of the most important tidal components is what we call the DE3 tide. In the astronomy lingo, DE3 really stands for D as in diurnal, so that means once per day. Eastward, so these features are moving east. And 3, that means there are 3 peaks and troughs around a latitude circle. Other important tides include the DW2, diurnal westward 2 feature, and DW1. Some of the modeling that I've done has been looking at what kind of signals will gold see due to these tides. So in this plot we have on the left the O5S, or the 135.6 nanometer oxygen color. In the middle we have the LBH color, and on the right we have the temperature anomaly due to just the tides. So you can see in the temperature that we have a variability of almost 80 degrees Kelvin, which is quite a lot, but the typical temperatures near 160 kilometers are already 625 degrees Kelvin. So it's maybe not quite as big as it seems. Furthermore, the oxygen and nitrogen emissions, which have plus or minus 40 and plus or minus 20 Rayleighs, which is how we count the brightness of those colors. This signal actually gets swamped by geomagnetic storms and high solar activity. So I'm one of the few scientists who's actually quite pleased that the sun is so quiet, because this is one of the rare opportunities that we can actually see these signals in Earth's atmosphere. Next we're going to talk about gravity waves. I don't want you to confuse gravity waves with gravitational waves, which is what the LIGO group is looking for, and black holes and whatnot. This is not that. These are gravity waves in Earth's atmosphere, and you take a parcel of air and you perturb it, and the restoring force is going to be gravity and buoyancy. This is a local wave, so it's really small and close to you. And they do play a very important role in transferring energy and momentum, even though they are very small, from the lower atmosphere into the upper atmosphere. A couple of the ways that gravity waves are created is through orography and deep convection. Now, orography is just a fancy way of saying wind blowing over mountains, so you can visualize how that happens. And deep convection is large thunderstorms or typhoons causing, when you have a large thunderstorm, it's basically this explosive energy up and out. And when you have an anvil on the top of a thunderstorm, this is when the thunderstorm has reached the boundary of Earth's troposphere, and it's like it's punching up into the stratosphere. and it looks like a pebble being thrown into a pond with the gravity waves that it emits. So next I'm going to show you a model of what gravity waves we think look like in the thermosphere or the upper atmosphere. I want to emphasize that it's a model. We don't yet have a way of globally visualizing what gravity waves look like. We can't measure them quite yet. We hope to get there one day, but we can't do it quite yet. So you can see all kinds of scales, all different types of things moving. This happens to be in meridional winds, which is north-south winds. You can also measure gravity waves in east-west winds, temperatures, densities. Pick a variable. One of the most prominent features you'll see in this movie is in the center of the movie there should be a feature of concentric circles flowing outwards. And that's actually due to a typhoon in the middle of the Pacific Ocean. And you can see this all the way up at the thermosphere at 100 kilometers in altitude. I'll let it come around one more time. I love watching this movie. There's the typhoon again. So in the GOLD mission, we're interested in possibly observing some of these gravity waves. We won't be able to see the full Earth like you saw in that movie of the model, but what we can do, because our slits are fully commandable, is what we can do is we can create an experiment. And on October 13th of last year, what we did is we parked both of those slits over South America because we thought that would be our best opportunity to see some gravity waves. The reason we want to park and stare is because gravity waves have such a small amplitude that they're really hard to see. So we need to stare for a long time and integrate a lot of time in order to get the signal to noise ratio at an appropriate level. So these are some results. I apologize, my axes have disappeared. On the x-axis should be time, so this is several hours of time. And on the y-axis, this is latitude. The red crosses are trying to indicate the wave-like features that we have observed with GOLD. These gravity waves are a special type of gravity wave we refer to as a traveling atmospheric disturbance, which is typically triggered by auroral activity. Although I also think that it could be triggered by activity off of the polar vortex, which is a band of high winds that circle the winter poles. All right, next we're going to talk about the equatorial ionospheric anomaly. I'm actually going to skip the physics behind how this works and just show you what it looks like phenomenologically. So the green line is the geomagnetic equator, and on either side of the geomagnetic equator you will see two bright bands of ionization or plasma. This happens to be also the color that shows up in 135.6 nanometers. What we have on the left is GOLD observations, I think from November 15th, 2018. And on the right is some modeling that I did with GLOW, and the underlying model is called TIGCM, which is the thermosphere ionosphere electrodynamics general circulation model, for those of you who are interested. And what you see is that it kind of did an inadequate job of modeling this particular phenomena. In the observations, we see two bright bands on either side of the geomagnetic equator, and they extend all the way across the Atlantic Ocean. We also see that they are pretty much symmetric, whereas the model showed a very asymmetric pattern. We did have some previous instruments, such as the GUVI mission and some ground-based measurements, to kind of guide us on what we might see, which is why we did perform these scans because we thought, well, maybe there's something there. Maybe we'll be able to see it. And sure enough, it was there. But the other thing these other instruments showed us was that we thought that there might be a seasonal dependence of the equatorial ionospheric anomaly, and that there might be something called bubbles. So more on what a traditional equatorial ionospheric anomaly looks like. These are some movies I'm going to show you that move with time, and this is because the slits actually scan small regions. And we're doing this because the brightness of this emission is pretty low, and so we have to stare for a longer amount of time to be able to get a good signal. So as the movie starts over, you can see it start on the left or right hand side. You can still see the two bright crests of plasma on either side of the geomagnetic equator. And then as time goes through the night, we follow it along. So what are these bubbles I keep talking about? Well, bubbles are basically regions of low plasma density surrounded by high plasma density. In this picture, you can see the warm colors as high plasma density, or lots of ionized gas, and the cool colors as low plasma density. And what can happen on this side, you can see there's a very strong gradient between high plasma density and low plasma density. You can have an instability form. And what happens is the high density plasma wants to be below the low density plasma. And so you have these plumes or bubbles of low density plasma that rises up. Now, you may think, well, that's very pretty and interesting, but what's the big deal? Well, the big deal is that these plasma bubbles interfere with radio communications and GPS. And when a signal coming from above hits this plasma bubble, it hits a strong gradient, and it wants to bounce all around. And you can actually lose lock on your signal. There have also been case studies, which I've cited here, of these plasma bubbles actually affecting battles that the US has been involved in Afghanistan. And basically, we lost communication with one of our helicopters that had Navy SEALs in it, and it resulted in casualties. So this is a big deal, and we don't fully understand why and when plasma bubbles form. And we're really hoping that through collecting more data with instruments such as gold that we'll be able to understand this better. All right, so what do plasma bubbles look like from gold? Well, you can see the strong ionospheric anomaly on either side, but what you'll see it developing are these bite-outs of those two strong plasma crests. They kind of look like tiger stripes to me, and they extend across the equatorial, or the geomagnetic equator. These happen to be plasma bubbles that happen at equinox. It's a well-known phenomena that the equatorial ionospheric anomaly is strongest at equinox, and we expect to see bubbles. But the thing is with gold, we've been through a solstice and 2 equinoxes with gold. We see bubbles all the time, and sometimes not at all. So we have bubbles that form over Africa, we have bubbles that form over South America, and we have bubbles that form over the Atlantic Ocean. What definitely surprised us is that we also see bubbles during solstice. So this is a period of time when the equatorial ionospheric anomaly is not well formed. And you still see these bubbles or tiger stripes forming. And the bubbles, you'll see them right at the end of this movie. They're starting to form there. You can sort of see them strongly there. Our Earth is illuminated by the electromagnetic spectrum, and we can view it in multiple colors and wavelengths. We happen to be viewing Earth in the far ultraviolet in this particular case. But from these emissions, we can detect waves that are percolating up from below. And we can also see bubbles that form. We really hope that this geostationary orbit will really revolutionize the way that we see space weather, and will really impact the way we mitigate impacts on our communications and navigation. Thank you. I'm willing to take questions if anybody has any questions. Sure.
I'm curious, how we predicted lifespan of this mission?
So there's a couple factors that go into this mission. The first is fuel for station keeping at geostationary orbit. And we had an anomaly on launch where basically we were launched into, I think, an 11.4 degree orbit when we should have been at 0 degrees, and we had to use up some of our fuel to get back to 0 degrees. But I think even with that correction, we still have over 30 years on board for the spacecraft. Now for the instrument, we have what's called burn-in on the detectors, and we can move the diffraction grating to try and extend the lifespan of that. So that's a little less predictable, but overall the spacecraft has at least 30 years of fuel.
Do you have problems with air glow at all? Being noise in your sensor and your data analysis?
What kind of air glow are you talking about?
Oh, basically, it's not like aurora, but you're basically seeing, in the lower atmosphere, different reds and greens.
So we don't really have that problem. We are capturing the full spectral wavelengths, and we focus on the wavelengths that we're interested in. And then the other thing is far ultraviolet light that's coming from below actually gets absorbed by the lower atmosphere, so we don't have to look at it.
What's your upper wavelength?
Quan, do you know that answer?
So what's that so she's talking about?
The upper wavelength that we see?
Both for UV and what I call optical.
UV, I think it's 160 nanometers?
Yeah.
I think it's 160 nanometers. Yeah.
Does the location the instrument is in matter at all?
You mean in geostationary orbit or in relationship to where it's placed on the spacecraft?
Geostationary orbit.
So it matters in that we only get to see approximately 1/3 of the Earth at any given time. So ideally, what we would really like to have is 3 of these instruments placed in geostationary orbit, evenly spaced around the Earth, so that we could see all the Earth at once. Because right now, we only get to see the Americas. And for example, if we're interested in what's happening over Afghanistan, we can't see that.
Do you have that plan in some future?
We always have plans. Whether or not there's money available is another question. Yeah?
So I don't know what it's called. This is talking about watching a sunset behind the Earth.
An occultation?
Yes. What is the purpose of doing it?
An occultation can give us vertical profiles in the atmosphere. So by watching a star or pinpoint light source set through the atmosphere, we can actually back derive constituent densities and temperatures. Yeah.
You said that the background, the lower atmosphere is opaque to the UV you're looking at. Is that opacity or even, or is it something that kind of varies and you have to compensate for?
What do you mean by even?
Well, I mean, so if it's a background, if it's absorbing in the background, is it absorbed evenly during at all times of the day and across all places on the Earth?
Basically, we're assuming that the atmosphere is well mixed and that well mixed atmosphere absorbs evenly. Yeah.
Causes the gravitational equator to vary the way it does?
You know, I think that is an active, open area of investigation. But you have you can imagine the magnetosphere, the magnetic protective layer around Earth as a donut, where the magnetic lines come out of the South Pole and go into the North Pole. But it's a little more complicated in that it's tilted and twisted. And so that's what causes the kink in the geomagnetic equator.
So if that's follow on, does that follow, does it move, does it shift?
So just as I believe as the geomagnetic north is moving, I believe the geomagnetic equator also has to move. Yeah?
If the team gets an opportunity for a follow-on goal,
Mhm.
essentially, what changes or upgrades to the payload might you try to make if you had another opportunity to fly?
Another opportunity. I think, from my perspective, that's really a good question for our PI, Richard Eastis. But I think what we might like is to add more channels so that we have more flexible ability to scan regions. So we could stare at one region with one channel and scan with the other channel.
Do you have any problems with the far ultraviolet trying to destroy or take apart your instrument?
So what we have is a situation called burn-in, where this is a little bit outside of my area of expertise, but basically over time the brightness of certain wavelengths is so bright that it degrades the sensitivity of the detector. And so we have to shift where the different wavelengths are imaged on the detector in order to maintain sensitivity.
You can physically move the detector.
It's the diffraction grating that's actually moved.
So you mentioned that people tended to say that you saw many bubbles during like eclipses and solstices, and then you said that you see them all the time. However, does that mean that there are more, like you see more during solstices and eclipses, or they're just present here?
I think what we're trying to say is that they're more prolific than we had originally thought. And I think it's because we just can see more and we can separate temporal and spatial variability. So that means that we can take a picture here and take the same picture again 30 minutes later. And so what we are able to do is follow the same bubble through multiple images. And we're able to see bubbles over places that we don't have ground-based instruments, so over the oceans, and so we're able to see more bubbles. I don't think that there are suddenly more bubbles since we launched. I think it's just that we're able to observe more of the ones that are there.
Your plasma bubbles, are they essentially ionized gas pockets?
Yeah, so I really like this graphic right here. So the warm color is high density ionized gas, and the cool colors are low density ionized gas. And so they're pockets, bubbles of low density ionized gas.
It doesn't look like they correspond a lot to like Earth sprites. Are they like an analog for that? Because you said there's this also symmetric set on the other side of the geomagnetic equator, right?
Yeah, I don't know a whole lot about sprites, to be perfectly honest. I've seen a lot of beautiful photographs of them, but I don't actually understand the physics behind them.
It's massive, like upstroke lightning kind of.
Right.
Have you correlated this with ground activity? Because the Amazon's really noted for having.
Right. So What we actually think they're correlated with is gravity wave activity, which is why I spoke about gravity waves. We think they seed the instability at the bottom of that layer.
So are you getting like a shear that opens up that weakness?
That initial pocket, yeah. Yeah. Okay. Thank you.